going to kind of run through this entire unit really quick just so it kind of makes sense. The repetitive nature of hearing this should help at least a little bit. But the main thing here, and again, I sound like a broken record, but like you should frame your mind around this concept right here. The slope of one point. That's the only thing that matters with this. That's the only thing that we're going to use to solve other types of problems. Okay. The first type was using derivatives to determine values of other things, whether it's Lhopitals Rule or linear approximation. Okay. So in your mind, think about it. How is derivative related to those two things? How can I use the derivative to find limits? How can I use the derivative to find linear approximation? Okay. Reflect on your understanding of these concepts. Hugely important. Okay, derivatives and graphing. Derivatives tell you certain things about what the original graph is doing. So you don't know what f is, but if you know what f prime is, you can use f prime to tell you some information about it. Okay, same with f double prime. Mean value theorem is unfortunately something that I have to teach you, but it just states that the slope of the endpoints equals, you know, some point in between, as long as the function is continuous and differentiable. And then real world applications like related rates, optimization, that sort of thing. You should be able to slowly use this as a visual aid to explain the entire unit. So you should be able to look at Lhopitals Rule and explain what that means. I do not overly explain things on these pictures, these images that I have here. You're meant to kind of make sense of it as you look through it. Okay, so it should all make sense, you know, by the 4th of March. The Lhopitals Rule: if it's 0 over 0, infinity over infinity, derivative over the derivative, do not use quotient rule. 312, instead of using the actual function, the curve, you can use the actual linear approximation, as it's going to be off by a little bit. Do not get tricked. If it's concave up, it's going to be an under approximation. If it's concave down, it's over. Okay? When in doubt, graph it. Oh, concave up, I can see that it's under. Even on both sides of it, it's underneath it. It's an under approximation. There is always going to be a question on that. Is this going to be an over or under approximation? It's usually in the free response. So make sure you're aware of that. Okay, increasing, decreasing. If the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. If the derivative is 0, then the original function is just constant. It's not increasing or decreasing. Okay. When it changes from positive to negative and the point exists, it's a relative max. The opposite is true for relative min. If it's negative to positive and it still exists there, it's a relative min. Critical numbers are where the derivative is equal to 0 or undefined. Do not forget the or undefined. Absolute extremum, make sure you test the endpoints. This is just a bunch of terms. Extrema means extreme values, relative min, relative max, absolute min, absolute max. Make sure you understand that. Concavity, if the second derivative is positive, it's concave up. It forms like a cup, holds water, if you want to think of it that way. If the water was like raining down on the graph. The second derivative is negative, it's concave down. If it's neither, it's 0, it's not positive or negative, it's linear. Where it changes sign, if that point exists, then it's called an inflection point, wherever the concavity changes. Mean value theorem just states, you know, if you have the endpoints of some graph, if you made a line between those two endpoints, it forms some slope. If it's continuous and differentiable, which this example it is, there's going to be at least one point that has the same slope. There's obviously another one over here, but I programmed Desmos to just find one because you can't do loops in Desmos for some reason. Modeling, this is derivative in context. I kind of renamed it, but the main thing is the units. F prime of x, it's whatever the units of regular f is divided by whatever x is. That's the units for it. Related rates, the main thing is it's implicit differentiation in the real world, and you're doing d over dt instead of d over dx. And the main thing is doing d over dt of both sides and then filling in the values and trying to solve. Optimization is just extrema. That's what we were doing before with the increasing, decreasing, the relative extrema here. Only it's with the real world things like fences and distance. Let's see here. Straight line motion, you have to know this. Position, derivative of position's velocity. Second derivative of position is also the first derivative of velocity's acceleration. And we haven't covered these problems yet, but they are in the practice problems. If an object is speeding up, it has to have the same sign for the velocity and acceleration. Slowing down, it would be the opposite. That's basically the entire unit in a nutshell. So what I want you to do is like continually be reflecting how well do you understand certain sections, which ones do you not understand, which ones do you need to work on more. You know, develop a plan in your head to work on those at specific times.